Covariance. What does covariance mean? First, let's see what the word covariance stands for. Covariance comes from co plus variance. So it kind of should mean vary together, or the variance of an interrelationship or related to each other. So it must be something related to relationship. Let's see what it means really. The covariance measures the strengths of the linear relationship between two numerical random variable x and y. So covariance is a measure of a strength of relationship, a linear relationship between two random variables. We have two formulas for covariance, covariance of samples and covariance in the population. For the sample, the covariance of x and y is computed using this formula. So here we have the average of x for random variable x, the average of y bar for the random variable y, and we divide it by n-1, which is the size of the sample. So here for the random variable x and y, we should have the same size of sample. The sample size for both random variable x and y is n. The formula for population covariance is kind of the same, except that instead of x bar and y bar, we have mu of x, which is the population average for x, and mu y, the population average for y. And we divide it by n, which is the size of the population, not by n-1. Only concerned with the strengths of the linear relationship. So it does only care about the strengths of the linear relationship, not about the nonlinear relationship. And the formula for in Excel is the covar parentheses x, random variable x, and random variable y. So what you do is you actually plug in all the arrays of x and y here. We're going to see an example for this. More about covariance. Covariance between two variables. If the covariance between x and y is positive, what that indicates? It indicates that x and y tend to move in the same direction. What it means? It means that if x increases, the value of x increases on average, the value of y would also increase. So the relationship is positive toward the same direction. On the other hand, if the covariance of x and y is negative, that means that x and y tend to move in opposite direction. So if x increases, y would decrease, or vice versa. If x decreases, y would increase. If the covariance of x and y is 0, that means that there is no relationship between x and y, no linear relationship between x and y. So the covariance has a major flaw. What is that? It is not possible to determine the relative strengths of the relationship from the size of the covariance. So what it means that if the covariance of x and y, for example, is 34, and the covariance of, for example, another two variable, x2 and y2, is 24, 25, these two values, you cannot compare them. It doesn't make sense to compare these two values. It's like comparing apples and oranges. So that's the flaw of covariance. The relative strength cannot be determined from the size. Coefficient of correlation. So we learned about one flaw for the covariance, and that is that it is impossible to make a conclusion about the relative strengths of a relationship between two variables based on the value of the covariance between the two variables. So coefficient of correlation is the medicine to that. The coefficient of correlation measures the relative strengths of the linear relationship between two numerical variables. Sample coefficient of correlation formula. R, we show the correlation of coefficient with R. And that's equal to the covariance of x and y divided by s of x, which is the standard deviation of x, and s of y, the standard deviation of y. So correlation of coefficient r and covariance, they are related actually, as you see in this formula. What it does here is r, the correlation of the coefficient of correlation, is equal to the covariance of the two random variable x and y divided by their standard, the multiplication or the product of the standard deviation, s of x and s of y. So in this formula, covariance of x and y, because we are talking about the sample, is this formula. And s of x is the standard deviation, which is this formula for sample x. And s of y is the standard deviation, which is computed using this formula. Features of the coefficient of correlation. The population coefficient of correlation is referred to as rho. This is called rho. It's like a tilted P. It's a Greek letter. So for sample, we show it by R, and for population, the coefficient of correlation is shown by rho. The sample coefficient of correlation is referred to as R. Either rho or R have the following features. They are unit-free. Their range is between -1 and 1. So both R and rho, they are between -1 and 1. That means that the smallest value that they can get is -1, and the largest value they can get is 1. So it's a value between these two. The closer to -1, the stronger the negative linear relationship between two variables. The closer to 1 plus 1, the stronger the positive linear relationship between two variables. And if the correlation of coefficient is closer to 0, that means the weaker the relationship, the linear relationship between two random variables. So now we have, that's why we call this a relative strength measure, because we know the limit of this correlation of coefficient. It's a value between -1 and 1. The utmost or the largest value that it can get, the strongest relationship positive would be +1, and the strongest negative relationship would be -1. So now we have an understanding, insight into the value of this measure, unlike the covariance. Let's see some examples of scatter plots of the various coefficient of correlation for some data sets. For example, these data sets. So here we have two random variables, x and y, and these are the data points. So for these data points, y and x are related. Why? Because as you see here, all of these data points can actually put on this line. You can actually find the formula for this line. So it's a linear formula, right? So y is a linear function of x. Y, for example, is equal to a, the intercept, plus b multiplied by x. B is the coefficient here, which is negative. So the relationship between x and y is linear, and because it's negative, so that's why r, the coefficient of correlation, is -1. It's -1, it means that it's the utmost negative linear relationship. And also, if you consider increasing on the direction of x, going from a smaller to larger value, what's going to happen is y is going to decrease, right? For example, this point, x is here and y is here. And if you increase x, for example, here, we have this point which y has decreased. So the relationship is strong, the most strong, but in the opposite direction. Let's see another example, which is not an utmost relationship. It's very strong, a little weaker. This example. So as you see here, all of our data points are scattered around the line, but they are not aligned on the line. They are scattered. So we don't have a linear relationship, but still the relationship is negative, because if you go from the increasing x, y is going to decrease. So r here is negative 0.6. Again, negative means the relationship between x and y is negative. If you increase x, y is going to decrease, and vice versa. And it's 0.6, it means that it's not very strong. It's weaker than 100%. Let's see another example. For example, this one. So this one, all of our data points are on the same line. So we have a perfect linear relationship between x and y. And also, it's in the positive direction. This means that if we walk onto the positive direction or increasing direction of x, y also is going to increase. So that's why we have perfect utmost positive direction relationship, +1. Let's see a weaker relationship here. This one, the relationship between x and y is not linear. They are scattered around the line, but they are in a positive direction. If you increase x, y is going to increase as well. So that's why it's positive 0.3. It's positive because it's x and y have positive relationship, and it's 0.3. It means that it's less than 100%. So it's not perfect. It's weaker. Right, so let's see another example. This one. So this one, although they look like on the same line, but honestly here, if you increase or decrease x, if you actually go in this direction or in this direction, y is going to stay the same. So y doesn't change. This means that although it looks like they all align on the same line, but they are not actually related. No matter what value of x is, y doesn't change. Y is the same, stay the same. That means that there is no relationship between x and y. So that's why r is 0 here. So this is an important example here. Make sure that you remember this. This is an example of when r is 0, when there is no relationship at all between x and y. We could have a closer relationship. For example, if these values would actually not align in the perfect line, we would have a value close to 0, but not perfectly 0. Let's see an example. The following is a set of data from a sample of n equal to 11 items. So we have 11 items for random variable x and random variable y. So you have to notice here that we have 11 items here for x and 11 number here for y. They have to be equal size, x and y. And these are the formula for covariance R and S of x. So as you see here, it would be a tedious way to find covariance here. So that's why we use softwares. So let's find the covariance between x and y. To find the covariance, first you need to find x bar, which this means that you have to find the average of these, x bar. And for also, you have to find y bar, the average of these values. And after that, you need to find the difference between x and x bar multiplied by the difference between y and y bar plus the next value. The difference between the next value and x bar multiplied by the difference between next value of y and y bar plus, and so on and so forth. So it would be a tedious computation. That's why we use softwares to do that. Thank God we have softwares. So after computing covariance, we have the formula for R, the coefficient of correlation. Here we have covariance of x and y in the numerator, and in the denominator we have S of x and S of y, which are the standard deviation for x and y, which you have the formula on the right. So let's find the covariance. I have computed the covariance using Excel. I'm going to show you. The covariance of x and y is 65.3. What does it mean? Because it's a positive value, this means that there is a positive relationship between x and y. But how strong this is, we don't know. We cannot tell from the value of the covariance. That's why we compute R, the coefficient of correlation, so that it would tell us the relative strengths of the relationship between x and y. So far, only thing that we know is that the relationship, the linear relationship between x and y is positive because the value of covariance is positive. So let's compute the coefficient of correlation, or R here. R equal to 1. That means that there is a perfect linear relationship between x and y. And if you look at the numbers here, you might actually see that. So x is 7, and the corresponding value for x is 21, which means that it has been multiplied by 3. 21 is 3 multiplied by 7. And you can see that in the next number. 5 multiplied by 3, that's 15. 8 multiplied by 3, 24, and so on and so forth. So there is a perfect relationship between x and y. In fact, y is 3 multiplied by x. So that's why the coefficient of correlation is 1. Next, how strong is the relationship between x and y? The strongest, very strong, because it's R is 1. But we couldn't tell that with covariance 65.3. Using Excel to find covariance and coefficient of correlation. So this is the formula for finding covariance. It says covariance, and then because we are working with the sample, it has .s here. That means sample. Find the covariance for sample. And then you put the values for the first random variable, for example, x, and then the second random variable, for example, y. And you separate them with a comma here. So let's see the previous example that we did here. And the correl is the correlation between x and y. So it's a coefficient of correlation, or R, sample here, R. R is correl in Excel, correl. So let's see the example here. We have the x values here. I have put them in separate cells here, as you see, y the same, and they are in the same size, 11 numbers. And then here we kind of find the covariance between x and y, which is covariance.s, then the values of x, which is starting from here, which is b3, to this value, which is L3, comma, then next values for y. So that would be the first value of y, which is 21, which is b5, to the last number, which is 54, which is related to L5. And we hit enter, and it gives us the covariance. The covariance is 65.291. Also, we can find the R, the coefficient of correlation. The function is correl, and we pick the same numbers. B3 to L3, that's B3 to L3, comma, B5 to L5. B5 to L5. And we hit enter, and we get the correlation equal to 1. So the coefficient of correlation is 1. Very simple to do with Excel. Next example. A study of 218 students at Ohio State University suggests a link between time spent on the social networking sites such as Facebook and grade points average, or GPA. Students who rarely or never use Facebook tend to have higher grade points averages in the study than students who used Facebook. Does the study suggest that time spent on Facebook and grade point average GPA are positively correlated or negatively correlated? So from the context of the problem here, it looks like that students who use the social networking website, Facebook, they never actually used it or rarely used it, they have higher grades. So if we define two variables, x amount spent or time spent, time on Facebook, FB, and y we define as GPA of the student, it looks like that as x increases, the value of x increases, this leads to decrease in y, the GPA. So this means that they have an opposite relationship or negative relationship. Less time on Facebook, less time is spent on Facebook, higher the grades. So they are negatively correlated. Let's see the next example. Do more educated people watch less TV or fewer hours of TV? Use the results of a 2012 survey as your sample to find this out. So we have a sample data, an Excel file that it's based on a survey conducted in 2012. The data is available on the website on our course page, and it shows the samples of data for two variables here. The first one is the level of education, which is actually years of education. So 12 means that they have a person has been to a school for 12 years. And the next variable is the hours of TV watched. So we're going to use these data to find the relationship between these two, whether the more educated people watch less TV or not. So we have the data for education in column A and the data for TV hours watched, hours in the second column. These are the two variables, education and hours, and we have these samples of data. So let's go ahead and find the correlation and coefficient here, the coefficient of correlation and covariance. First, covariance. So the covariance between education and TV hours watched. So these two are equal to, since this is a sample, I'm going to use .s, and then the first array has to be, for example, for education here. So I'm going to pick all the values here. We need to see how many values do we have here. We have 1,299. So this has to be 1,299. And for the TV watch would be B2 to B 1,299. Right. And this is the covariance here. I can put this here. This is just the numbers, and I'm going to do this so that you would see it. This is the formula. All right. So the value for covariance is negative 1.7273. That means that they have opposite relationship or negative relationship. That means that the higher the education, the less TV they watch. We can also find the coefficient of correlation. I'm going to show it by R. R of education and TV hours. So this is equal to, the function is Corel, and let's use the same value. So that would be A2 to A 1299, and for TV watch would be B2 to B 1299. So this is the coefficient of correlation, and that value is negative 0.19, or about 20%, negative 20%. So this also shows that there is a negative relationship, but the relationship is not that strong. It's a weak relationship. It's a weak negative relationship, but it still is negative. So congratulations, this is the end of our lecture.